You must have written C++ code like this. It looks perfectly reasonable because we're using a const reference to string, so there's no copying of the string. But when you pass a string literal directly to the process log function like this, can you really say that nothing extra is happening? Not necessarily. When you pass a string literal to a const reference to string, C++ may need to construct a temporary string first. That is, before you even enter the function, the string may have already been converted, constructed, and may have incurred additional memory operations. A similar problem exists in another very common operation, taking substrings. For example, you just want to extract 20 characters from a large string using this line of code, but the substr function creates a new string and copies those 20 characters over. If this operation is performed only once, it's not a big deal. But if you're writing a parser, processing logs, parsing network requests, or building a server that handles thousands of requests per second, these seemingly minor copies and allocations can become real performance costs. So what if I just want to take a look at the string rather than owning it? What can I do? C++17 provides a very simple answer, string view. The concept of string view is actually very simple. It is not a string, it's more like a window. It only records two things, a pointer and a length. So when we write this code, no second copy of the string is created. The only copy of the data remains in memory. String view stores a pointer pointing to the character h and stores a length telling it, starting from here, look at 11 characters. So what it sees is the string hello world, but it does not own those characters. This is the most important difference between string view and string. This also means that creating a string view itself does not require copying the string and typically does not require heap allocation. This is especially important for substring operations. Suppose we have a string. If we use a string object and want to extract a portion, the program needs to create a new string and copy quick into it. But if we use string view, it's much simpler. It only needs to change two numbers, move the pointer to q, and change the length to 5. That is, the underlying string hasn't changed at all. The string view just went from viewing the whole thing to viewing only a part. This is why substr operation of string view can be O1. We can do a simple comparison, perform 10 million substring operations on both string and string view. The result, string substr, takes about 0.816 seconds, while string view substr takes only about 0.018 seconds. The gap is about 45 times. And when the substring length keeps increasing, the gap becomes even more significant. But this is not the most valuable part of string view. The really interesting use case is parsers. Suppose you're parsing a string and you need to split it into several words. The traditional approach is to use a container to store all the substrings. Every time you produce a token, you create a new string object. So on top of the original string, many new strings appear. Each token may involve new objects, new data copies, and additional memory management. But if we save each token as a string view, the situation is completely different. All tokens can point directly to the original string. They are just different windows over the original string. There's no need to copy any characters. This is why string view is perfect for parsers, log processing, and various string slicing operations. But at this point, you might be thinking, since string view is so fast, should I replace all strings with string view from now on? Quite the opposite. This is the most dangerous part of string view. Because it does not own the data, you must be very clear about how long the data it points to will live. For example, this code on the screen, it looks like there's no problem. The function returns a string view. But the problem is that name is a local variable. After the function ends, it is destroyed. But the string view still points to the original memory, even though the string no longer exists. If you continue to use this view at this point, it's undefined behavior. So using string view requires following a very important rule. It cannot outlive the data it is observing. There's another particularly tricky pitfall. This line of code is also very dangerous. Because the string is a temporary object. After this line ends, the temporary string is destroyed. But view still holds a pointer to it. So what you get is a dangling string view. There's another easily overlooked issue. String view does not guarantee null termination. For example, in this code, string view now sees the string hello, but the underlying memory may still be hello world, followed by a null character. View only records that the length is 5. It does not place a new null character after hello. So if you print this string, there's a problem. Because the %format specifier requires that what you pass in must be a C-style string terminated with a null character, but string view only guarantees a pointer and a length. So if a function explicitly requires a null terminated string, you cannot simply pass string view s_data function to it. When necessary, you need to create a new string object. So string view is not a faster string. They actually serve different responsibilities. String owns the data. String view borrows the data. If a function only reads the string and does not need to save it, string view is often a good choice.